We started the semester talking about stars and basic constellations and how we started to see about motions of stars. So this kind of led us into some ideas about stars and the nature of stars. But one thing that we needed to do was be able to look at the light of stars, because that's all we really see. So we'd started chapter 17, and then we went back to chapter 5 and 6 to talk about light, nature of light, and the telescopes. Now we're back into chapter 17. So we want to look at the spectrum of stars, and we already said that by looking at the Doppler shift, we can see if stars are coming towards us or going away from us. If they're blue shifted, they're headed towards us. If they're red shifted, they're heading away from us. Well, we know that the tangential velocity of stars can be given by the parallax. Remember, mu times d gives you the tangential velocity. The radial velocity is what you get if a star is Doppler shifted. Now, if you have both, that means the star is not just going away from you, it's also going to the side, and so it's really doing this sort of thing. And so you want to be able to say, well, what's the star really doing? And so to do that, well, we've got the tangential velocity, which is the side-to-side motion. We've got the radial velocity, which is the motion away, and they're right angles to each other. So if you want to add things at right angles, we use Pythagorean theorem. So that would be the radial velocity squared plus the tangential velocity squared. And then we take the square root of that sum, and that gives you the actual velocity. Now, if you want to know what angle is it moving, then that comes from trigonometry. So what we do is we say the angle that it's moving is the arctangent. So that's the inverse tangent of the tangential velocity, the side-to-side motion, divided by the radial velocity. Sorry, that should be VR right there for radial velocity. Okay, so there we have these equations, and you're not going to have to do this, but it can be done, and that would allow you to figure out how these stars are moving in space, what direction they're moving, and how fast they're moving. And so that turns out to be very, very important, because we know that our sun is just a star in the midst of a bunch of other stars out here. And some of them have radial velocities, some have tangential velocities, so that means they're all moving around. Some are getting farther from us, some are coming closer to us. One interesting little thing that we find is that there's this one star, it's got several different names. It's number 710 on Gliese's list of little dim red stars, but it's also BD minus 1 degree 3474 in the Barnard-Muxtering catalog. Right now, it's not much of a star. It's a little small red star. It's currently close to 50 light years away. Its magnitude 9.66, so that's dim, barely visible in binoculars if you got really dark skies. But it's coming towards us almost straight at us. There's almost no side-to-side motion. There's a little bit, but not much. And so it's moving at 24 kilometers per second. So in about 1.4 million years, it's going to be about a light year from the sun. Now, why is that important? Well, the Oort cloud, which is this cloud of icy objects around the solar system, that comets come from. If something disrupts the orbit of an Oort cloud member, it will dive in close to the sun, become a comet. So when it is 1 light year away, remember that's more than 4 times closer than the current nearest star, which is well over 4 light years away. And so that means it's going to be much closer. It'll be only magnitude 1.2. Now, 1.2 magnitude, first magnitude, that's pretty bright. But considering that this star is going to be super close, that's still not very bright, which means this is a very tiny little star. But the Oort cloud goes out to about half a light year or more, which means that it's going to be so close, the gravity of this thing will definitely disrupt the Oort cloud, and there'll be a rain of comets into the inner solar system. Now, why is that interesting? Well, if you have to be around in 1.4 million years, then that means the entire sky will have comets. I mean, probably more than one naked eye comet visible at any given moment for hundreds of years maybe. Now, that would be really cool to have all these comets visible in the sky, but the problem is all these things flying around randomly means it's very likely that one of them will run into a planet. Well, Earth is a planet, so that means there's actually a pretty decent likelihood that we might have either a near miss or an impact from a comet. So now the good news is we've got about almost 1.5 million years to plan for this and to come up with some kind of planetary defense mechanism, which means if Congress starts working on it right now, then in about 1.5 million years, they may agree on the furniture in the conference room where they discuss the budget on how to go about establishing a defense for Earth. Okay. All right. So, by looking at the spectrum and looking at the Doppler shift, we were able to figure out the radial velocity, and by doing some mathematics, combining this with what we already learned about tangential velocity and proper motion, we're able to measure the motion of stars and calculate where they were in the past and where they're going to be in the future. So this is a major tool. Next thing I want to talk about is actually looking at the spectrum of a star and looking at what that really tells us about the nature of the star.